Hello everyone, welcome to lecture series on power system protection. Myself Rajeshwari Nananavar, working as an assistant professor in the Department of Electrical and Electronics Engineering, KLS VDIT Haliyal. Today we are dealing with second module, lecture number 13. In previous lecture, we discussed the distance protection, that is the introduction to distance protection. What is the meaning of distance protection? So actually these distance protections were used for the protection of the transmission line. So as we have already discussed, the overhead transmission line are exposed to the environment, so more and more fault occur on the transmission line. So the better protection system need to be provided for the transmission line. So for extra high voltage transmission line or a simple high voltage transmission line, so the protection is very important. So the protection which is provided for such transmission line is known as a distance protection. So the term distance comes here because these relays are going to operate based on the distance between the point where the relay has been located as well as the where exactly the fault is. The distance between these two, it is going to consider, hence the name distance protection. In that the various categories we have, the first we consider the impedance relay. Okay, so the name itself suggests these are the relays which are going to operate based on the values of the impedance measured between the points where the fault occurs and the point where the relay has been located. Between those 2 points it is going to measure the impedance. If the impedance of the line is less than a particular value, say constant value, so the relay is going to operate. If it is greater than that, the relay is not going to block or the relay is not going to operate. So in operating principle, so we discussed, so the two torques will be produced. One is a operating torque because of the current and one more is a restraining torque because of the presence of the actuating quantity voltage. So the torque equation what we had was K1 I square minus K2 V square minus K3. So that K1 I square is because of the current and K2 I square is because of the voltage. So the relay is going to operate as and when the K1 I square is greater than the K2 V square, that is the operating torque is greater than the restraining torque. So with that, if I consider the ratio of V by I as a Z, so it should be less than some constant value K. Okay, so if I represent the characteristic of that, it is going to give me a circular nature. So inside the circular nature, whatever the area is there, in that area, inside the circle having a radius of K, if any fault occurs and impedance lies between that value, so the relay is going to operate, and outside the circle the relay is not going to operate. And also we discussed the stepped time distance characteristics, where for a one section of the line protection, instead of providing a complete 100%, so we'll be dividing it into the three zones. The first area or the first zone, it provides only 80 to 90% of the protection. The second zone will provide up to 50% of the protection, as well as the third zone which will be acting as a backup protection, or it is consisting of the first line plus second line plus the 25% of the remaining line. So like this we'll be having the stepped nature characteristic in this impedance relay, hence the name stepped time distance characteristic. So these were the points what we had discussed in the previous class. Moving on to the today's class, today we are going to discuss the another two types of a distance protection scheme. The relays which is used in the distance protections are the reactance relay and Moore relay. So after this lecture, the students will understand what is the construction of the reactance relay, Moore relay, what is the operating principle of these relays, and how the characteristic is going to define the operation of these reactance relay as well as the Moore relay. So construction, operating principle and characteristics of the reactance relay as well as the Moore relay, the students are going to understand. As per the Bloom's taxonomy, the today's concept comes under the second level, understanding level L2. The first will begin with the reactance relay. What is the meaning of reactance relay? So before going for that, as we have already discussed in the previous class, that is the impedance relay. Okay, so there we discuss it is going to measure the distance between the 2 points, that is the point where exactly the relay has been located and the point where the fault has been occurred. Between these two distance, it is going to measure the impedance of the line. So that impedance is combination of a resistance and reactance. Okay, so for that we term that as a impedance relay. Similarly, the reactance relay, the name itself suggests reactance, means it is a relay which is going to decide or which is going to measure the reactance of the line between the 2 points, that is where the relay has been located and where the fault has been occurred. Between those 2 points, it is going to measure the reactance. So as we know that impedance is nothing but a combination of resistance plus reactance. If I remove that resistance from the impedance, so we left out with only reactance. So these reactances are going to measure only the reactance of the line because of the presence of impedance, that is because of the presence of the inductive coil or because of the presence of capacitors. Okay, so removing that resistance part. Okay, so it is not including the resistance into account. A reactance relay measures the reactance of the line at the relay location and it is not affected by variations in the resistance. Whatever may be the variation of the resistance of the line, it is least bothered. It is going to measure only the reactance. Okay, so the X part it is going to measure. In case of a fault on a protected line, the measured reactance is a reactance of the line between the relay location and the fault points. Its characteristic on a RX diagram is a straight line parallel to R axis as shown in the figure. So as we don't have any resistive part over here, so this resistor will not come into picture. So whatever the characteristic I am getting, it is simply a parallel line which is straight line parallel to the R axis. Okay, so whatever may be the value, so R, it is least bothered about the value of R, it is going to give me a constant value of X. Okay, and below this characteristics it is going to trip, and above this characteristic line it is going to block. So as we already discussed for the impedance relay, there we got the characteristic as a circle. So inside the circle it is going to trip the relay, and outside, if fault occurs outside the circle, the relay is not going to operate. Similarly, so this parallel line, below this parallel line the circuit breaker is going to trip, whereas for the above the characteristic line the relay is going to block the relay. Operation of the relay is not happens. So this is the characteristic of the reactance relay what we observed. Okay, and this is about this characteristic we'll explain later. So this is a reactance relay with a starting unit characteristic. So later we are going to discuss about this. So the construction of these reactance relay, considering a electromechanical reactance relay. So again, induction cup type reactance relay we are considering here. So as we have discussed in the induction type of relays. Okay, so here it is surrounded by a 4 poles, upper pole, lower pole. Okay, this is a right hand side pole and this is a left hand side pole. Okay, so this is covered with the help of a 4 contacts, 4 poles, and this is a relay consisting of the contact, and here we have provided one phase shifting circuit. Okay, so the function of this circuit is to provide the phase shift as and when required. So here these upper and lower poles will be energized by a quantity, input quantity I, current I, whereas this quantity is energized by a voltage, so that is voltage. Okay, so these are the 2 operating quantities. So because of these two, the 2 different types of the torques are going to be produced. Okay, so how it is going to operate, let's see. An induction cup type structure shown in figure 3C is used to realize the reactance relay characteristic. The torque equation of the relay is given by T is equal to K1 I square minus K2 VI cos 90 minus phi minus K3. Okay, so this K1 I square, it is produced because of the presence of the actuating input quantity current, as I have already told you, to the upper and lower, and this quantity is produced because of the input quantity voltage. So this is a restraining torque produced, K2 VI cos 90 minus phi, and this is a K3 because of the presence of the control springs. Okay, so if I solve this, again simplify this equation, I am going to get K1 I square minus, instead of cos 90 minus phi, I can replace it with the sin phi. So K2 VI sin phi minus K3. The current produces a polarizing flux in the upper and lower poles and also in the right hand side pole. Okay, so whatever the actuating quantity current which is flowing through this, it is going to produce the polarizing torque, that is a operating torque in the upper as well as in the lower poles, at the same time it is also going to produce the polarizing torque in the right hand side of the pole. Okay, right hand side pole. The flux in the right hand side pole is out of phase with that in the upper and lower poles because of the secondary winding, which is closed through a phase shifting circuit and is placed on the RHS pole. Okay, so whatever the flux it is going to produced here in this right hand side pole, it is closed with a phase shifting circuit. So because of presence of this, the flux produced by this, it will be out of phase as compared to the upper and lower fluxes. So the flux in the right hand side pole is out of phase with that the upper and lower poles because of the secondary winding, which is closed through a phase shifting circuit and is placed on the right hand side pole. The interaction of the polarizing flux and the flux in the right hand side pole produces an operating torque K1I square. So because of these interaction of the polarizing flux and the flux in the right hand side pole, so when these two interacts each other, so they are going to produce a operating torque known as a K1I square. The winding placed on the left hand side pole produces a flux which interacts with the polarizing flux to produce the restraining torque. Okay, so the poles which are produced on the left hand side, so these are energized because of the voltage. Okay, so the flux produced because of these voltage interacts with the polarizing flux and it is going to produce the restraining torque proportional to Vi cos 90 minus phi. So the angle between the actuating quantities which are proportional to V and I. So here we have taken the actuating quantities as a current and voltage. So the angle difference between these two quantities can be changed to realize the desired characteristics. In this case, the angle between actuating quantities is kept 90 minus phi. The relay operates when K1I square is greater than K2 Vi sin phi. Okay, so this is the basic principle what we are considered for the relay operation. As and when the operating torque is greater than the restraining torque, the relay is going to operate. So here also the operating torque K1I square, when it becomes greater than the restraining torque K2 Vi sin phi, the relay is going to operate. And neglecting K3, which is a constant for the spring's torque. Thus we have, so here I can have this K1I square greater than K2 Vi sin phi. Thus if I rearrange the terms, I am going to get V by I sin phi is less than K1 by K2. Okay, see, simply I have rearranged the terms here. Okay, V by I sin phi less than K1 bar K2, or V by I can have it as a Z, that is the impedance term, into sin phi less than K. Or this entire term I can represent it as a reactance. So as you already know, when the term comes with a sin phi, so that we can represent it as a reactance. So when X is less than K. Okay, so the relay is going to operate. X is nothing but the reactance of the line, transmission line, what we have considered for the protection. So if the reactance of that transmission line is less than some constant value K, the relay is going to operate. Okay, then the characteristic of the reactance relay on the RX diagram is shown in figure 3. It will operate when the measured value of the reactance is less than the predetermined value K. It is not a non-directional relay, as it will also operate for a negative values of X, that is in the reverse direction also. A directional unit having a circular characteristic is used in conjunction with reactance relays and also acts as a 3 unit of the distance scheme. So here comes the characteristic which is shown here. Okay, so this is a operating characteristic. As I told you, when the reactance of the value is become less than some constant value K, so it is going to operate, it is going to trip. As and when this reactance value is more than the K value, it is going to block the operation of the circuit breaker. And this is going to represent the 3 zones of the protection of the reactance relay. So as we have already discussed in the previous lecture also, the 3 zones we have provided for the protection of the line. The first is going to protect up to 80 to 90%, the second zone will be protected up to 50%, and the third zone will be up to combination of these plus 25% of the third line. So here also the same thing here we have considered. So in a circular fashion we have taken the 3 different zones here, zone 1, zone 2, zone 3, that is the percentage protection level is also mentioned, 80%, 50% and 25%. Okay, so this is a characteristic reactance relay characteristic with a starting unit. Okay. Now, moving on to the first unit is a high speed unit to protect 80% to 90% of the protected line, as I have already told you. The second unit protects up to 50% of the adjacent line. The third unit is a backup unit to protect the whole of the adjacent line. So, this is how the characteristic represents the three zones. First zone is up to 80 to 90%, second zone will be up to 50%, and third zone is again a combination of first and second plus 25% of the third, or it will be acting as a backup protection. So, this is how the reactance relay is going to measure as and when the distance between the 2 points, that is a relay operating point as well as the fault occurrence point. Okay, if the reactance of this reactance of this transmission line is greater than some constant value, relay is going to block the operation. If the reactance value is less than some constant value K, then predetermined value or the preset value, whatever we can say, if it is less than the measured reactance is less than the predetermined value, so the relay is going to operate. So, this is how the reactance relay is going to operate. The main important thing here we need to understand what is why the name termed as a reactance, because it is going to measure the reactance of the line between the 2 points where the relay is being placed as well as where the fault has been occurred. Hence the name reactance relay. So, under normal condition with a load of high power factor, the reactance measured by reactance relay may be less than its setting. Such points have been shown in figure 3 by P1 lying in the first zone of protection and P2 in the second zone. To prevent false trippings under such condition, the reactance relay should be supervised by fault detecting unit, which limits its area on the RX diagram. Hence, its characteristic should be a circular one. With this type of a directional unit, the reactance relay will not trip under conditions of a high power factor load. Next, we will move on to the Mo relay, the another type of a distance relay which is used for again the protection of the transmission line. The term Mo comes here. The another name for this Mo is nothing but the admittance. Okay, so the Mo relay measures a component of admittance, that is Y at an angle theta, magnitude as well as angle. Its characteristic when plotted on the impedance diagram, that is the RX diagram, is a circle passing through the origin. It is inherently a directional relay as it detects the faults only in the forward direction. Okay, so it is going to measure the faults only in the forward direction. It is also called an admittance or an angle admittance relay. Okay, so another name for these relays is a admittance relay or an angle admittance relay, because here it is operating with respect to the angle. It is called a Mo relay because its characteristic is a straight line when plotted on an admittance diagram. Okay, so usually we need to plot them in a RX diagram. So if I take reverse of that, RX the reverse, if I draw, it is going to give me the GB, that is the admittance diagram. Okay, so when I plot the characteristic on that, it is going to give me a straight line. Okay, so as we already know, the admittance is nothing but the inverse of the impedance. 1 by Z is nothing but the admittance that we are representing with the help of a letter Y. So Y is nothing but a inverse of the impedance, that is admittance. 1 by Z, that is represented with the letter Y. Now coming to the construction of this electromechanical Mo relay, again the same induction cup type construction we are using in order to give the protection with respect to the Mo relay, as we have already in case of used in case of a reactance relay. The same relay has been used as a Mo relay also. So an induction cup structure as shown in figure 4b is used to realize the Mo relay characteristic. The torque equation is given by, again, T is equal to K1 Vi cos phi minus alpha minus K2 V square minus K3. So one important difference here you need to make a note that in previous reactance relay, so here the left hand side pole is energized with a voltage, but here it is energized with a current, And whereas in case of reactance relay, these upper pole, lower pole as well as these right hand side poles were energized with the current. Now here it is energized with the voltage. So the actuating quantities are taken in a opposite direction. Okay, so they have replaced. Okay, wherever we had a voltage, now we have a current, and where in case of a reactance relay, where the voltage was there, here we have taken that quantity as a current. Okay, so that is a one difference you need to make a note. Okay, so because of that construction only, the entire relay can act as a Moore relay. So the torque is given by K1 Vi cos phi minus alpha minus K2 V square minus K3. The upper and lower poles are energized by a voltage V to produce a polarizing flux. The series capacitor provides a memory action. The left pole is energized by a current, which is the operating quantity. Okay, that is the only one difference which is going to make the difference between the reactance relay and the Moore relay. The flux produced by I interacts with the polarizing flux to give an operating torque K1 Vi cos phi minus alpha. The angle alpha can be adjusted by varying the resistance in the phase shifting circuit placed on the left pole. Okay. The RHS pole is energized by voltage, produces a flux which interacts with the polarizing flux to produce a restraining torque K2 V square. So this is how the two torques will be produced. One is produced because of the I interacting with the polarizing flux, which is going to produce the operating torque of K1 Vi cos phi minus alpha, where this angle alpha is nothing but the angle between the two quantities, which is adjusted with the help of a phase shifting circuit. The RHS pole is energized by voltage, produces a flux which interacts with the polarizing flux to produce a restraining torque K2 V square. Okay, so this is going to produce the restraining torque K2 V square, and this is going to produce the operating torque K1 Vi cos of phi minus alpha. Okay, so moving on to the principle, as we know that the operating torque should be greater than the restraining torque. So the relay will operate when the operating torque is greater than restraining torque. So this is my operating torque K1 Vi cos of phi minus alpha, which is greater than K2 V square, the restraining torque. Or we can have it as I by V. So this V gets cancelled. So I by V, if I take this V to this side, okay, so I by V cos of phi minus alpha as it is should be greater than K2, and this K1 will come over here. So K2 by K1. Or I by V, that is we can have it as a Y. As we know that V by I is nothing but the impedance Z. The inverse of that, I by V, is nothing but the admittance Y. Y cos of phi minus alpha should be greater than K2 by K1. Or in turn I can rearrange these terms as 1 by Y cos of phi minus alpha less than K. I have taken the inverse. Here it will be K2 by K1. I can have that simply a K. Or 1 by Y is nothing but the Z. 1 by admittance again is nothing but the impedance Z divided by cos of phi minus alpha less than K. Or M, mu is less than K, some constant value K. So that entire Z upon cos alpha minus phi minus alpha, I have taken it as a M, a constant M less than the constant K. Okay, so the mu is less than K. So like this, the operating condition. Okay, so the relay is going to operate as and when the M is less than K. The 3 units of Moore relays are used for the protection of a section of the line. Okay, so the first unit is a high speed unit to protect 80% to 90% of the line section. Second unit protects the rest of the line section and its reach extends up to 50% of the adjacent line section. The third unit is meant for backup protection of the adjacent line section. The second and third units operate after a preset delay, usually 0.2 seconds to 0.5 second and 0.4 second to 1 second respectively. So these already we have discussed in the previous lecture for the impedance relay. The second unit is going to operate after a preset delay time of 0.2 seconds to 0.5 second, and the third unit or the third zone of protective relay is going to operate after a preset delay time of 0.4 seconds to 1 second respectively. So this is the same construction what we are using, the first unit, second unit and the third unit. First unit for the 80 to 90%, second unit is up to 50% of the adjacent line, and the third unit is meant for the backup again it is going to provide the adjacent line section. Okay, so the operating time of the second and third unit is also provided. The connection diagram of a Moore relay unit placed at a one location is shown in the figure. Okay, so how we can place the, or how we can have the connection diagram of this Moore relay. Okay, so this is a connection diagram what we have for the Moore relay. So here these are the T2, it is a timing contact. These are the relays what we can say. Here we have a sealing relay, here we have a sealing relay coil and the trip coil, and we have a circuit breaker auxiliary switch, and here we have a timing unit, and these are the flags. Okay, now what is the meaning of each term in this circuit diagram? Okay, now whenever a relay operates, okay, as and when it is going to the Mo value, that is the admittance value is less than some constant value, so the relay is going to operate. Okay, when that relay is operate, its flag indicates its operation. Okay, so we'll be providing a flags, so those are going to indicate the operation of those relays. So these M1, M2, M3, as and when they operate, they are going to indicated by these flags. Okay, so for that purpose we were using those flags. A sealing relay, okay, which is used, a sealing relay is used to bypass the contacts of the main relays to save their costly and delicate contacts. So here we'll be using the 3 units now. So in order to provide protection, or in order to save the contacts of the main relay, instead of M1, M2, M3, if there is a main relay contact, in order to prevent those main relay contacts, okay, which are very costly and very delicate contacts we have. Okay, so in order to protect that, we need to bypass the contacts of the main relay. Okay, so we need to bypass unnecessarily. It should not trip again and again, it should not close its contact again and again. Okay, in order to bypass those main contacts, so these sealing relays are going to be used. Once the contacts of the main relay are closed and the current passes through the trip coil, the coil of the sealing relay is energized. So this is a sealing relay coil. Once the main relay contacts, so this is going to close and it is going to energize the trip coils. The circuit breaker auxiliary switch. Okay, so this is a circuit breaker auxiliary switch. What is connected here is normally a closed switch. Basically it will be a closed, as indicated in the circuit diagram, it is basically a closed switch. When the circuit breaker tips, the auxiliary switch is opened to prevent the unnecessary drainage of the battery. As and when the circuit breaker is switches, the main circuit breaker connected to the line opens, okay, or it is energized, this circuit breaker is going to operate. Okay, so this switch is going to open its contact to prevent unnecessary drainage of the battery. Okay, so these are the different components what are there in the Moore relay construction. Okay, so this is a timing unit, this T2, okay, which is provided for the second, and this is a T3. I have forgot here, this is a T3, that is a timing contacts of the M2 as well as M3, which is going to operate after a preset time period, or as already mentioned, 0.2 to 0.5 second or 0.4 to 1 second. Okay, so these are the timing contacts, which after that only those relays are going to operate, and this is a main timing unit what we have, which is going to energize after a preset time. Okay, so this is a connection diagram what we have for the Moore relay. Similarly, the same connection diagram we can have for the reactance relay as well as the impedance relay also. Please go through those diagrams also, a connection diagram of impedance relay as well as the reactance relay. So this is about the Moore relay, which is used to protect the transmission line as well as and when the admittance of the line is less than a particular constant value. If it is less, it is going to operate. If the Moore relay or the Moore admittance value is greater than the constant value, it is not going to operate. So this is a basic of your Moore relay. And finally, moving on to the summary of the today's section. So today we discussed the two different types of a distance relays. So one is a reactance relay and another is a Moore relay. In reactance relay, we discussed why the term reactance, because it is going to measure the reactance of the line, as and when the reactance of the line becomes greater than the constant value, the relay is going to block, or relay is not going to operate. When the reactance value is less than a predetermined value, it is going to operate, the relay is going to operate. So its characteristic, it is a parallel to the R axis, because it is not considering any effect of the R. Okay, simply it is measuring the reactance of the line. and also we discussed the Moore relay, which is nothing but the admittance relay or the angle admittance, because it is indirectly dependent on the angle, so it is also called as a angle admittance relay. Okay, its characteristics also we discussed, and connection diagrams also we discussed. So these are the two distance relays for today's section, and tomorrow we are going to deal with again one more type of a distance relay, that is an angle impedance relay. So based on this concept, you may get the question, what is a reactance relay? Explain the operating principle and the characteristic. Along with the characteristic graph, Rx diagram graph, okay, you need to explain what is the meaning of reactance relay and what is a Moore relay, why the term Moore relay. You need to explain first. Explain the operating principle and characteristic. Those two talks will be produced with the help of those construction, induction cup type construction. You need to explain the operation. So these are the two questions you may expect in the question paper, and for this you can refer the textbook. Thank you. Have a nice day.